How do you sort a million numbers fast? The answer has been the same since 1959, quicksort. It picks a pivot. Pivot can be either center element, left or right element, partitions everything around it, then conquers each half recursively. Simple idea, devastating speed. Let's watch it work on this array of 8 numbers. We're using the last element as our pivot each round. Quick note, choosing the last element as pivot is simple, but it's also quicksort's Achilles heel. Feed it a sorted array and this strategy hits worst case every time. Round 1. Our pivot is 8, highlighted in blue. The J pointer scans left to right. Whenever it finds something smaller than the pivot, I advances and we swap. Every tick on that counter is one comparison. Watch how fast it climbs. 8 is now in its final position. Everything to its left is smaller. Everything to its right is larger. That's the power of partition. Now we recurse into the left side. New pivot, same process. The sorted positions lock in one by one. Each recursive call narrows the window. Fewer elements, fewer comparisons. The array converges. And there it is, fully sorted. Let's talk about what that just cost us. Best case, the pivot splits the array perfectly in half every time. That gives us O of n log n. Average case, with random data, we still expect O of n log n. This is what you get in practice on most real-world inputs. Worst case, O of n squared, happens when the pivot is always the smallest or largest element. Sorted input with a last element pivot is the classic trap. Space-wise, quicksort is in place. It sorts inside the original array. But the recursion stack costs O of log n on average and O of n in the worst case. Here's why the average case is O of n log n and not something worse. Every call to quicksort eventually calls partition, and partition always does n comparisons across its level of the tree. At depth 1, we have 2 subproblems. Together, they still touch every element once. That's n comparisons total for this level. Depth 2, 4 subproblems, still in comparisons across the whole level. The tree has log n levels when splits are balanced, and comparisons per level, log n levels. That's where O of n log n comes from. The recursion bottoms out when low meets high. Nothing left to sort. Now let's map what we just saw to actual code. The quicksort function is just 3 lines of logic. Check if there's more than one element, partition it, then recurse on the left and right halves. Partition starts by pinning the last element as pivot. The I pointer tracks the boundary between small and large elements. It starts just before the active window. J scans every element. If it's smaller than the pivot, I steps forward and we swap. This slowly pushes all smaller elements to the left side. When the scan is done, the pivot slots into position right after I. That index is returned. It becomes the split point for the next 2 recursive calls. Let's bring it all together. Strategy, pick a pivot, partition in place, recurse on both halves. Average time, O of n log n, fast enough for almost anything. Worst case, O of n squared, avoidable with better pivot selection like median of 3 or random pivot. Space, O of log n. It sorts inside the original array, which makes it extremely cache-friendly. Best used when you have large, randomly ordered data sets and memory efficiency matters. Quicksort isn't just fast in theory. Decades of real-world use have proven it's one of the most practical sorting algorithms ever written. That's it for today. Thank you for watching.